Have you ever stopped to think about how strange hydrogen really is? We often hear that hydrogen is the fuel of the future. We hear about hydrogen trucks, hydrogen cars, hydrogen airplanes, and entire hydrogen economies. But there is one number that quietly appears throughout the industry that almost nobody outside engineering ever questions. 700 bar. It appears on fueling stations. It appears on vehicle specifications. It appears on storage tanks. It appears in technical reports. And yet most people never ask the obvious question, why 700 bar? Why does hydrogen need such extreme pressure just to be useful? The answer takes us into one of the most fascinating hidden engineering stories in the hydrogen economy. It is a story about physics, space, pressure, materials, energy, and the invisible compromises that make hydrogen transportation possible. Today we're going to follow that story from the first molecule all the way through the hidden systems that allow hydrogen to become a practical fuel. When most people look at a hydrogen fueling station, they see a truck, a fueling dispenser, and a storage tank. Nothing appears unusual, yet sitting behind that fueling process is an engineering reality that is completely different from gasoline or diesel. The tank sitting beside the station may contain hydrogen at 700 bar. To put that into perspective, atmospheric pressure around us is only about 1 bar. That means the hydrogen inside that tank is being stored at roughly 700 times atmospheric pressure. The immediate question becomes obvious. Why so much pressure? Why would an energy carrier require such extreme conditions just to operate? The answer begins with a hidden property of hydrogen that creates challenges throughout the entire industry. Hydrogen is remarkable because it contains a tremendous amount of energy by weight. 1 kilogram of hydrogen contains roughly the same usable energy as a gallon of gasoline. That sounds incredible until you discover the problem. Hydrogen has excellent energy density by mass but terrible energy density by volume. In simple terms, hydrogen is light, extremely light. If you take 1 kilogram of hydrogen and leave it uncompressed at atmospheric pressure, it occupies an enormous amount of space. The energy is there, but it is spread out across a huge volume. This single reality drives nearly every engineering decision in hydrogen transportation. Imagine comparing 1 kilogram of hydrogen with 1 kilogram of gasoline. The energy content is surprisingly similar, yet the physical space required to store them is dramatically different. Gasoline fits comfortably into a small container. Hydrogen at normal pressure expands into a massive volume. The molecules are simply too far apart. This is the invisible problem that sits at the center of the hydrogen economy. It is not that hydrogen lacks energy, it is that hydrogen takes up too much space. Now imagine trying to build a hydrogen truck using hydrogen stored at normal atmospheric pressure. The storage volume would become absurd. Instead of a practical fuel tank, you would need a giant trailer-sized container. Just to hold a relatively small amount of fuel, the truck would spend most of its space carrying the fuel tank rather than carrying cargo. Range would be limited, efficiency would suffer, transportation economics would collapse. The fuel itself would still work, but the system around it would become completely impractical. This is why normal pressure hydrogen is not suitable for most transportation applications. The solution is not to change the hydrogen, the solution is to change the space between the molecules. Compression allows engineers to take the same hydrogen molecules and move them closer together. Nothing about the chemistry changes. Nothing about the energy content changes. What changes is the amount of space required to store the fuel. As pressure increases, molecules occupy less volume. The same amount of hydrogen can fit into a dramatically smaller container. Compression transforms hydrogen from a scientific curiosity into a practical energy carrier. This process can be visualized as a journey through pressure levels. At 1 bar, hydrogen molecules are widely dispersed. At 30 bar, they begin moving closer together. At 100 bar, density increases significantly. At 350 bar, the storage system becomes practical for many heavy-duty applications. And at 700 bar, hydrogen reaches a density that allows passenger vehicles and long-range transportation systems to become commercially viable. Every step upward on the pressure ladder reduces volume while increasing storage capability. The higher the pressure, the more hydrogen can be carried within the same physical space. But if higher pressure is beneficial, why stop at 700 bar? Why not 1000 bar? Why not 2000 bar? This question leads us directly to the engineering compromise at the heart of modern hydrogen mobility. 700 bar is not simply a technical achievement. It is a carefully chosen balance point. Engineers discovered that around this pressure level, hydrogen storage becomes practical for passenger vehicles while remaining achievable from a manufacturing, safety, and cost perspective. Going lower creates range limitations. Going significantly higher creates escalating engineering challenges. The difference between 350 bar and 700 bar is especially important. At 350 bar, tanks must be larger to store the same amount of hydrogen. Larger tanks occupy more space inside the vehicle. That means less room for passengers, cargo, and other components. Range is reduced because the amount of hydrogen that can be carried is lower. At 700 bar, the storage system becomes much more compact. More fuel can fit within the available volume. Vehicles can travel farther. Passenger vehicles become realistic products rather than engineering demonstrations. This is why many modern hydrogen fuel cell vehicles rely on 700 bar storage systems. However, pressure is never free. Every increase in pressure comes with a cost. Compressing hydrogen requires energy. Large industrial compressors must perform work to force hydrogen molecules closer together. Electricity powers these compression systems. Some of that energy becomes stored pressure. Some is lost through heat generation, mechanical inefficiencies, and system losses. The simple act of compressing hydrogen consumes energy before the fuel ever reaches a vehicle. This means hydrogen infrastructure is not just about producing hydrogen, it is also about investing energy into making hydrogen compact enough to transport. As pressure increases, another challenge emerges: heat. Compression naturally generates heat. Anyone who has used a bicycle pump has experienced this phenomenon on a small scale. Hydrogen compression operates on a vastly larger scale. Temperatures can rise significantly during compression. Excess heat must be removed through cooling systems. Engineers use intercoolers, heat exchangers, and sophisticated thermal management systems to control temperatures and protect equipment. Without these systems, efficiency would decline and component lifetimes would shorten dramatically. Then there's the challenge of leakage. Hydrogen is the smallest molecule in the universe. Its tiny size makes containment difficult. At 700 bar, hydrogen constantly seeks pathways through seals, fittings, valves, and microscopic imperfections. Even extremely small leak paths can become important over time. Engineers must develop advanced sealing technologies and material systems capable of containing hydrogen under extreme pressure conditions. This challenge is one reason hydrogen systems require specialized engineering compared with conventional fuels. Material stress becomes another major concern. At 700 bar, storage systems experience enormous forces. Every wall, fitting, connection, and structural component must withstand repeated pressure cycles over many years of operation. These forces are not occasional events. They occur every time a vehicle is fueled and every time pressure fluctuates within the storage system. Fatigue, stress concentration, and long-term durability become critical design considerations. Hydrogen embrittlement introduces an additional layer of complexity. Certain metals can become weakened when exposed to hydrogen over time. The hydrogen atoms interact with material structures, potentially reducing toughness and increasing susceptibility to cracking. This phenomenon forces engineers to carefully select materials throughout the hydrogen value chain. Storage systems, valves, compressors, pipelines, and connectors must all be evaluated for hydrogen compatibility. The fuel itself influences the design of the infrastructure. To overcome these challenges, engineers developed advanced Type FUI storage tanks. These tanks represent some of the most sophisticated pressure vessels used in transportation. They are not simple metal cylinders. Instead, they use multiple layers that work together as a system. At the center is a polymer liner that acts as a gas barrier. Surrounding that liner is a carbon fiber composite layer that provides the primary structural strength. Outside the composite is a protective shell that helps defend against environmental damage and physical impacts. Each layer serves a specific purpose. Together, they create a lightweight vessel capable of safely containing hydrogen at 700 bar. The carbon fiber layer is particularly important. Carbon fiber offers exceptional strength while remaining relatively lightweight. Traditional steel tanks capable of handling comparable pressures would become extremely heavy. The use of carbon fiber enables practical vehicle applications while maintaining the structural integrity required for extreme pressure storage. The result is a storage system that combines high performance with acceptable weight characteristics. Yet, even with advanced tank designs, the question remains: why stop at 700 bar? Why not continue increasing pressure to achieve even greater storage density? The answer lies in diminishing returns. As pressure increases beyond 700 bar, storage density continues improving, but the improvements become smaller while costs rise rapidly. Tanks require additional reinforcement. More carbon fiber is needed, compressors become more expensive. Energy consumption increases. Safety requirements become more demanding. Engineering complexity rises faster than the storage benefits. At around 1,000 bar, the industry enters a zone where costs and complexity begin increasing disproportionately compared with the gains in storage density. The additional hydrogen that can be stored often does not justify the increased system burden. Engineers therefore view 700 bar as a practical compromise. It provides strong storage density, reasonable vehicle range, manageable infrastructure requirements, and proven safety performance. It is not the maximum pressure possible. It is the pressure that balances competing objectives. When viewed from a systems perspective, the importance of 700 bar becomes even more apparent. Production facilities generate hydrogen. Compression systems increase its density. Storage systems contain it. Refueling stations dispense it. Trucks transport it. Ships move it between regions. Industrial facilities consume it. Fuel cell power plants convert it back into electricity. Throughout this entire ecosystem, pressure serves as the invisible link connecting the pieces together. Without effective compression and storage, the broader hydrogen economy becomes far more difficult to implement. This is why 700 bar is much more than a technical specification. It is an enabling technology. It is one of the hidden foundations that allows hydrogen mobility to exist. Behind every hydrogen vehicle, behind every fueling station, and behind every transportation network sits a complex chain of engineering decisions built around this single number. 700 bar represents a compromise between physics and practicality. It represents a balance between density and cost. It represents a solution to hydrogen's greatest transportation challenge: volume. And perhaps that is the most important lesson from this story. The future of energy is not shaped only by new fuels. It is shaped by the hidden systems that make those fuels useful. Hydrogen may capture the headlines, but compression, storage, materials, engineering, and pressure management are the technologies quietly doing the work behind the scenes. They are the invisible machinery that transforms hydrogen from a molecule into a functioning energy system. If you want to explore the entire hydrogen ecosystem from production and compression to storage, transport, fueling, industry, and power generation, visit H2Hub by Renee Energy and ReneeEnergy.com, where we break down the hidden systems behind the hydrogen economy and the engineering realities that make the future possible.